This video is really about Chapter 1 of Greenberg. It's an introduction to differential equations. Much of what I'll talk about are the various key terms that you'll need to understand when we discuss differential equations. And then I'll talk briefly about Introduction to Modeling. This is a section of Greenberg, and it really covers some of the decisions one needs to make mathematical representations of real physical systems. After viewing this video and doing some of the problems in the problem set, you will understand what is meant by the solution to a differential equation, and you'll understand clearly the relationship between the solution and the differential equation itself. You'll also be able to recognize different characteristics of differential equations in order to sort of characterize the different types of differential equations that you may encounter. And then the last objective for you is you'll learn to appreciate the differences between an approximate mathematical representation and of a system and the real system itself. So let's consider a differential equation, and it's one that you work with on a routine basis. For example, dx dt is equal to v, where x as a function of t is a position, and t is time. And in this equation, the right-hand side is v, and let's say v is a constant speed. So this is a differential equation relating how, describing the rate change of position with time, and it's described as a constant. So if you know how fast you're going, the speed you're going, you'll know how far you can travel in a certain amount of time. So let's solve this equation. And one simple way of solving it is we can separate the dependent variable, which is x, on the left-hand side of the equation, and the independent functions of the independent variable on the other side of the equation, and then we can simply integrate. And this tells us that x, as a function of t, this is the solution we seek, is equal to v times t plus a constant, which, in this case, it is the starting location. It's the location, it's your location when t is equal to 0. Okay, so that is that's a simple solution to a very simple differential equation that you probably encounter at least at some level as you drive to work or something like that. Okay, another example is covered on page 1 and 2 of Greenberg. Is based on Newton's second law, which is F of force is equal to mass times acceleration. And if you recall from physics, the acceleration, I'm going to write this on the left-hand side of the equation, is the second derivative of a position with respect to time. And so this is a second-order differential equation. And this can be solved just as we did above by simply by integrating. Okay, so it's a relatively simple equation because all we have to do to solve this is to integrate. But what about the following? Suppose we have our mass and our acceleration, and then suppose we have an additional function, and in chapter 1 this relates to this is a mass on a spring, where this is the spring constant, which describes, well, this term is the force. If you have a mass attached to a spring, the force is proportional to how far the mass has been moved, because it stretches or compresses the spring. And then we have an imposed force, an external imposed force on our mass. So how do we solve this? We could try by integration. And so we could do, for example, we can, if we integrate, let's see, if we integrate with respect to time once, we'll get something like m dx dt. We're integrating both sides of the equation with respect to time. And so we have kx dt is equal to the integral of f of t with respect to t. And so we can solve this one. We can evaluate that integral simply just as a variable, as I did. We can evaluate this if we know what the forcing function is, but we cannot evaluate this integral because we don't know what x of t is. Okay, so the branch of study called differential equations is the study of how to solve problems such as this one. So let's talk about some definitions. So a differential equation we used to call this diff-EQ when we were studying differential equations, or I can abbreviate it as DE for a differential equation. And a differential equation is an equation containing one or more derivatives of a function or the function we seek to solve. So when we have one or more derivatives of a function, in the previous case, the function was x. Here we have we have a second derivative of x. If we have a function involving derivatives, then the branch of study used to solve those types of equations is called differential equations. Now, let's talk. So the function we seek is often called the dependent variable. Whereas the independent variable and there could be multiple independent variables control the behavior of the dependent variable. And so in the previous example, the dependent variable was x, and the independent variable was t, time. An ordinary differential equation abbreviated as ODE, involves derivatives with respect to only one independent variable. So this equation, F equals ma, it was an ordinary differential equation because the only dependence was on t, or time. A partial differential equation or a PDE involves derivatives of more than one independent variables. Or I should say, with respect to greater than one independent variable. And I should have written independent variable above. So for example, right, so this is where partial derivatives are describing or the function or the equation that we seek to solve. So an example of, we just talked about an example of an ordinary differential equation. An example of a partial differential equation is the diffusion equation, which describes the diffusion, for example, of heat, U, as a second derivative, proportional to a second derivative with respect to space, controlling how that heat, or whatever is diffusing, changes with time. As you take more classes in physics or engineering or geoscience, this diffusion equation will you'll see this diffusion equation a lot. It's a very extremely important equation to natural phenomena. Now the order of the differential equation is the number or the order of the highest derivative. It's the highest derivative in the equation. So, for example, the diffusion equation involved a first order partial derivative and a second order partial derivative. So the order of this equation is 2. So we would refer to this equation as a second order partial differential equation. And an n order differential equation a differential equation of order n will have n integration constants or n conditions on the independent variable that needs to be satisfied. Those conditions must be defined at the onset and satisfied to give the appropriate solution. And that describes the order of an ODE. The solution of a differential equation is the function of the dependent variable, for example, x of t, that when substituted into the original equation reduces the equation to identity. So, for example, in our very first, very simple example, we said that x is equal to our constant velocity times t plus x naught. And so this is our function of our dependent variable. And the original equation was dx dt is equal to v. And to verify that this is a solution to this, we would simply take the derivative of x with respect to t and from this equation, and we would see that it's equal to v. And so, well, we see that we've recovered our differential equation, but formally we would insert v for dx dt in our original equation, and we would see that v is equal to v, which is an identity. It's an equation that gives an identity. So indeed, this is a valid solution to this original differential equation. So the next definition is that of an initial value problem. An initial value problem is a problem in which a condition of the solution is given at one point of the dependent variable. Or it's specified at one point. So for example, we had our original equation dx dt is equal to v, and let me plot the various solutions. Actually, right, remember we had the solution, well, a solution was x is equal to v times t plus x naught. Remember, when we integrated, we have an integration constant, and so there's really an infinite number of solutions to that, depending on what that integration constant is. And so one can sketch the family of a family of solutions. Where representing different starting points, right? So an initial value problem, in this case, the initial value problem specified the point, the position at t is equal to 0. And so an initial value problem would specify x at t equals 0, or it could specify it at any other time, just so long as it's specified at a single point. And I'm just now recognizing I should it's not only one condition, it could be multiple conditions. So in general, there are one or more conditions that need to be specified at one point. The key is one point. Now, if that one point happens to be at the start of the calculation, or the start of the simulation, then that would describe the initial condition, for an initial value problem. And that contrasts with the next definition, which is a boundary value problem. Which is a problem in which conditions are specified and met at more than one point. For example, the two boundaries of a model domain. So an example of this type of problem would be, for example, the steady state diffusion problem. So remember, the original diffusion equation described a diffusion in space equaling a change in heat with time, but for steady state, there's no time dependence. It's a constant distribution of heat. And to solve this for a certain amount of diffusion, we would need, for example, to define the conditions of U on two boundaries. In other words, we need to define the boundary conditions. Or I should say that if the problem is phrased such that conditions are defined at two boundaries, then that makes this a boundary value problem. Now, a linear differential equation involves linear functions of the dependent variable and its derivatives. If there's a function that involves nonlinear functions of the dependent variable and its derivatives, then it's nonlinear. So a linear differential equation, or in this case, a linear ordinary differential equation, has the form of the following. So I'm going to write the nth derivative of y first. And I'll put the n in parentheses just as Greenberg does to denote the nth derivative, followed by a linear function of the n minus 1 derivative, followed by another function, a linear function of the n minus 2 derivative. And so the term that's being multiplied by each of these is, well, denoted p, and these are functions of the independent variable. So in this case, the dependent variable is y, the independent variable is x, and the p's are functions, general functions. They could be linear or nonlinear functions, but they're because they're of the independent variable. And all the way down to the nth coefficient on the first derivative, or I'm sorry, the 0th derivative on y, which is just y. And that's all equal to a function that's independent of y, and only a function of x, for example. So linear DEs are easier to solve. I should say linear ODEs are easier to solve, and often can be using analytical methods. An analytical solution is simply a solution that you can write out with a pencil and paper. It's something you can write out in closed form. A nonlinear DE involves nonlinear functions of the dependent variable. And these are harder to solve and often treated with either approximations. It's surprisingly hard for me to write and talk at the same time. Often solved using approximations or numerical methods. And using a computer. So numerical solutions are approximations to the mathematical equations that are solved on a computer, and we'll talk about that later. And so in much of the next couple of weeks, we'll deal with linear OD. Well, this week and the next, we'll deal with solving linear ordinary differential equations. Okay, so for an example, let's look at an example. If we have the third derivative of y plus x to the fifth times y equals sine of x, this indeed is a linear ordinary differential equation. It's an ordinary differential equation, again, because y only depends on x, or the derivatives are only with respect to x. and they're linear functions of y or its derivatives. In contrast, if we had the second derivative, well, the third derivative of y plus x to the fifth over y is equal to sine of x, this is a nonlinear ODE because we have a nonlinear function of y. A homogeneous ordinary differential equation is one in which the part that's not dependent on y or its derivatives is 0. So remember our general form of our linear ODE. This is a linear ODE. So the part that was independent on y is we move that to the right-hand side, and a homogeneous ODE involves the part that's independent of y equaling 0. So the right-hand side equals 0. If that is the right-hand side, if we reduce our ODE to this form, and then correspondingly a non-homogeneous ODE means that the part that's independent of y, or the dependent variable, is non-zero. Now the significance of this term is often sort of interpreted or modeled as a forcing function to the solution. And the example that I'll bring up is our Newton's second law equation, in which we have the mass times an acceleration equaling an external force. So this is a function that's independent of x, and it's the force that drives acceleration and motion of a body.